So, hello everyone, this is lecture 8 for the atomic physics. In the last lecture, we were studying about the orbital magnetic moment and the orbital angular momentum. So, we studied about that. In the last, I told you that how orbital angular momentum or the magnetic moment interact with the spin magnetic moment, and there will be this magnetic field. So, let's explore it more. And today, we'll study about the spin magnetic moment and the total magnetic moment or the angular momentum. Before that, let me tell you one thing. Now there is when there was no magnetic field produced, so that the space was same, means it was isotropic. Isotropic means same in the all direction. But see, when there is this magnetic field produced due to this electron rotating, then this isotropy will break and there will be the particular direction in which there will be magnetic field. And if we call that direction as the z direction, then there will be particular direction for L and mu L. So you will get something like this. Means when you have the magnetic field, let's call the direction as z. You have some direction at theta angle. This is your angular momentum for the electron. And opposite to that, you will have the magnetic moment as we already discussed. Now see, there will be this magnetic moment and there is this magnetic field B. So you already studied in the physics in the previous classes that there will be a torque produced because of the magnetic moment and the magnetic field, that is given by torque equal to m cross b. In that case, we discuss magnetic moment as m. So here it is mu l. So mu l cross b will give you the torque, and torque will result in the rotation of this particular magnetic moment vector. And similarly, this is opposite to this L, so that's why this both will gyrate or gyrate, I will say. That is called a precision, means they will rotate around this. Now if they are rotating, then there will be some frequency with which they are rotating, that is called the angular frequency, and here we call that frequency as Larmor frequency. So Larmor precision will give you Larmor frequency, and formula for that frequency is nothing but omega L equal to GL E by 2m and B. So this frequency doesn't depend on the theta, so it is independent of theta, and it will depend only on the gyromagnetic ratio and the magnetic field. So that much you must remember this. So let's see. When we place orbital magnetic moment vector L in a magnetic field B, then it experiences a torque that is mu L cross B, which is always perpendicular to mu L and B. Due to this torque, this mu L vector gyrates about the B direction as shown in the figure. This is everything which I already told you. The figure, as L is opposed to mu L, it also gyrates about the magnetic field with same frequency. This frequency is called the Larmor frequency, omega L, and we already seen the expression for that. This frequency is independent of theta, that is, it doesn't depend on the orientation of L. With respect to z direction, it only depends upon field intensity and gyromagnetic ratio. So we discussed this. Now let's start spin magnetic moment. See, there is nothing like electron is spinning on its axis. It is just in the school days we told students just to get them idea. But here there is nothing rotation like that. There is some intrinsic property inside the electron that gives out this magnetic moment. And why we get this, means why we consider this as a magnetic moment. So there is reason behind that. Means there was two scientists, that Back and Goldsmith, introduced electron spin to explain following two spectroscopy observations particularly. So why they introduce? See, if you have some atom and that have one electron system, or the valence electron is only one in that atom, so and that is present in the s orbital. So S will give you nothing but L equal to 0, and if L equal to 0, then there will be no magnetic moment should be there, and it must have the diamagnetic nature. That means there will be no magnetic moment. But see, if we find in some that kind of atoms, we find that they are not diamagnetic, they are paramagnetic, and we find a net magnetic moment inside them. So from where this magnetic moment is coming? So that is from the spin magnetic moment. So this was the first thing. The S state with orbital angular momentum 0, L equal to 0, have no orbital magnetic moment. Therefore, in one electron system, if this value electron is in S state, then mu s must be 0. For this electron, this type of atoms should be diamagnetic. However, it's find out that they are paramagnetic. So to explain this, they consider that there will be some spin magnetic moment of the electron. And second is the splitting of many spectral lines, means we get the splitting of the many spectral lines, means we get several lines in the presence of weak magnetic field. We will discuss them later. So this can't be explained again if we don't consider this spin magnetic moment. So external field cannot be explained without introducing electronic spin. Now, electron spin is the intrinsic angular momentum, as I told you, associated with the electron. It has nothing to do with the actual rotation of the electron. Rather, it is somehow associated with the internal degree of freedom associated with the electron. Now this spin also behaves like the angular momentum, so this we call it as a spin angular momentum, and we will write the expression same as for the orbital angular momentum. So there was L and magnitude was LL plus 1 h cut, so here S will be SS plus 1 h cut, and again spin is half, so there is nothing like minus half and plus half. It will be spin always will be written as half, And what is minus half and plus half? That is according to the z direction. We will define that it is parallel and anti-parallel. That's why we define it as plus and minus. But in general, there is a spin that is only half. There is nothing like minus half. Now this must have the formula same as for the magnetic moment also. That is minus gs e by 2ms. But see this g factor or spin g factor for this spin magnetic moments. So that will be 2.0023. So it is generally 2 given by the Dirac. But there is this correction term 0.0023. This is because when electron have the spin, there will be some radiation or the electric field, and some fields will be there. So that's why there is this correction term in the GS. So this is the correct value. So that's how you can calculate the magnetic moment also for the spin. On the basis of relativistic quantum mechanics, this small correction 0.0023 is due to interaction of electron with its radiation field. Now see, magnitude will be under root ss plus 1 h cut. So here if s is half, then this will be root 3 by 2 h cut. So you can just substitute the value for the magnetic moment also. So it will be for s, in place of s we will write under root ss plus 1 h cut. So it will be e h cut divided by 2m this. So this is nothing but Bohr magneton, and it will be just mu b. So this is your formula for the magnetic moment. As s is angular momentum, its z component is also quantized. Now again, as we have seen in the L, that is orbital angular momentum, that is also quantized in z direction. So this must also be quantized in the z direction. So let's find the z component of the this magnetic moment. So that will be mu s z. That will be given by gs e by 2m sz. So again, sz is also quantized. So that will be ms h cut. In the quantum mechanics we see these expressions. So now ms, as s is half, so you will just minus 1 of half, that will give you minus half. So ms can take only two values, that is plus minus half. So you will say that why don't we have other values of spin, only plus and minus half. So see, you will see in the Stern-Gardic experiment, that is the proof that there will be only two possible spins, that is plus minus half. So in that experiment, we just see that there is beam of electron that is passed through the magnetic field, and you will see the splitting of the beam in the two directions. So that is the proof of this spin. So you can check on the Google about that. So mu s z will be minus gs e h cut by 2m. Now this will be your, this is again Bohr magneton, and this is your value. So this will give you in the z direction, this will give you two values, that is plus gs mu b and minus gs mu b divided by 2. So that will be two values, and these are called the parallel and the anti-parallel spins. So mu s will be, again we can just write this mu s, this is complete magnetic moment, that is substitute as in place of s, that is half, and gs 2. So that will give you on root 3 mu b. So sometimes you will get this kind of term also in the exams. Now the possible orientation of the electron spin. In the z direction, we will see that we have mu s available and mu s z available. So we'll just check about the theta. So that will give you this, as z is nothing but s cos theta. As z is nothing but s cos theta. So cos theta will be s z by s. So we are just checking that how much orientation it can take in the space. So cos theta will be sz by s. So sz is ms h cut. This is ss plus 1 h cut. H cut will cancel out. So ms will be plus minus half, and s is half. So this will give you two values of theta. That will be 54.7 and 125.3 degree. So these are the two thetas available. So these two orientations of s are possible in the space. So this is called a space quantization. Now according to this, this will be your magnetic moment in the z direction, that is half h cut. And according to this, it will be minus half h cut. So these are the two z components are possible for the spin magnetic moment, and these are called the parallel and the anti-parallel. So that's how now you are getting the two components. So this will result into the splitting of the lines, as we will see. So this was a very great development. Now see, this is also a angular momentum, and we have seen for the orbital also. So these both are the angular momentum, so they can combine by such means. Means if any means are possible inside the atom, then they can means interact with each other. So or can be added. As L and S are both angular momentum vectors, so they can be added vectorally if they have some means of interaction. Now see, what is the means of interaction here? As I already told you, there is this magnetic field which is interacting with this spin. So there is this means of interaction in magnetic field. So that's how we can just add them, and we can find the final or the total angular momentum. And that is can also be written in the same formula as we discussed for the L and S. In atomic physics, they interact through the magnetic processes. So this J is called the total angular momentum, as it is again representing angular momentum quantity. So it will be quantized in magnitude. We'll just write the same formulas for this also. In the orientation with respect to z direction. So J will be again Jj plus 1 h cut. So this is very easy to remember now because we are having the similar formulas. So total angular quantum number. Now again it is also quantized in the z direction. So Jz will be mj h cut, and mj will be minus j2 plus j. And if we want to find the components or how it is oriented, so jz is nothing but j cos theta, and cos theta will be jz by j. It will be mj by jj plus 1. So first we need to find the j, then we can find mj, and we can find all the possible orientations of j. So see, j is nothing but L plus S, so jz will be Lz plus Sz, and now we can just write jz as mg h cut, ml h cut, ms h cut. Now see, if you have simply this, then this will be S will be half. There is nothing to say about this. But if we find the z component, then for the spin we will have two components, that is plus minus h cut by 2. As we discussed here, there will be two components in the z direction for S. So for one L, you will find that there will be two possible S, and that's how you will get two different values of j. So mj is ml plus s, so j will be l plus, means ms is nothing but plus minus half. So for the z component only you are getting two components, so that's why for single value of l you will get two different values of j. So for one value of l we will have the two different value of j for one electron system. So that's how we explain the splitting of the lines. Now you will see that how we write the spectral terms. See, for L equal to 0, there will be nothing to interact with, means there is no orbital magnetic moment, so there is nothing interaction. So writing plus minus half with the 0 makes no sense. Okay, there is nothing like that, means something should be there in the place of L, only that can interact with the spin. So that's why there is only half term is there, means single term is there. There is no splitting in the ground state or the when L equal to 0, or there is this electron in the s orbital. So for L equal to 0 or s orbit, j will be simply half. Okay, it will be written as s half. So we will see that how can we write these spectral terms. This is nothing but L, means if you have L equal to 0, it will be s p d f. For the means when you have the multi electron system, then you will write them in capital, but when you have single electron system, then you will write this L in the small letters, L and S, means SPDF, and it will be capital for the multi electron system. And here this m is nothing but multiplicity, that is given by 2s plus 1. This s is nothing but spin, and this j is the total angular momentum, which we calculate from here, and this n is the total, means the principal quantum number. We will see about this. So how they are splitting, see, for L equal to 0, it will be plus minus half, so it will be simply half. As I already told you, there is nothing such like plus minus half here in the when L equal to 0. So no coupling, L equal to 0, only this one spectral term will be there, s half. But for P, L equal to 1, it will be 1 plus minus half, means 1 plus 1 by 2, 1 minus 1 by 2, that will give you half, and 3 by 2. So there will be splitting, and that will be in the two terms spectrum, that will be P half and P 3 by 2. Again for 2, it will be 2 plus minus half, it will give you 3 by 2, 5 by 2, D3 by 2, D5 by 2. For 3, it will be this 5 by 2, 7 by 2, so these will be two terms. So they will all split into two spectral terms, and we can write these spectral terms in the form of this, but it will be 2, so it will be simply 2f5 by 2, 2f7 by 2. That's how you can calculate. So we'll move further in this discussion more, and we'll see you in the next lecture. Thank you everyone.